For part A, we know that Hooke's law is the force of the spring is equal to negative k times x, and the fx graph would be a linear line going down because the a is replaces the x, so if there's a negative a, that means the force has to be positive, and when there is a positive amplitude, the force of the spring has to be negative. For part B, the axis t graph would look like a negative cosine graph, because initially the block starts at negative a, and as the block is released, it goes to positive a. And the v of t graph, the points would be v max and negative v max, and the graph would look like a sine graph because initially the velocity is 0, and when it's released, the velocity is pointing towards equilibrium, which is right, so it goes to v max positive. And the a of t graph the points would be a max and negative a max, and the graph would look like a positive cosine graph because initially the acceleration is positive because it's pointing right, for C, we know that MEI is equal to MEF, and breaking it apart, we can get PE spring at its max point is equal to the KE at its max point, and breaking it up, we can get kx squared over 2 is equal to NV squared over 2, and we cancel out the 2 on each side to get kx squared is equal to mv squared, and we can divide m on each side to isolate for the v. So v squared is equal to kx squared over m, and we take the square root of each side to cancel out the v squared. So the v max would equal to x rad k over m, and for the x, we can replace x with a for the amplitude. So the v max would be a rad k over m, and doubling the distance, the v nu max would be 2a rad k over m. So I would agree with the student's claim that doubling its amplitude would double its max velocity because the amplitude is on the outside and not inside the rad. In part D, we know that frequency is equal to 1 over t, and omega is equal to 2 pi over t, and we can multiply by t on both sides and divide by omega on each side to isolate for t. And from the previous problem, we know that V max is equal to A rad K over M, and know that V over A is equal to omega. So we can divide both sides by the amplitude to get omega, and the A would cancel on this side. So omega would equal to rad K over M. And we can plug the omega back into the period function to get 2 pi over rad K over M. And we can flip it to get T is equal to 2 pi times rad M over K. And we can plug it into the frequency function to get 1 over 2 pi times rad M over K. And we can flip the rad MK, and frequency would equal to 1 over 2 pi times rad K over M. And the student claims that doubling the amplitude would change the frequency, but I would disagree because distance doesn't appear in the frequency formula. For E, we know that MEI is equal to MEF. And breaking apart, we get PE, the spring at max, is equal to KE plus the potential energy of the spring. And breaking it up even more, we get K A squared over 2 is equal to MV squared over 2 plus KX squared over 2. On the right side, the potential energy uses X because the distance can be anywhere, while the potential energy on the left side uses A because at potential energy of the spring at max, the distance is A. And we can cancel out the 1/2 on each side to get KA squared is equal to MV squared plus KX squared. And we can move the KX squared into the left side. And we can factor out the K. And we can divide by M onto both sides to get K over M times A squared minus X squared is equal to V squared. And from the previous problem, we know that omega is equal to rad K over M. And we can square both sides to get omega squared is equal to K over M. And we can plug K over M as W squared. And we can square root both sides. And while square rooting omega squared, we get V as plus or negative omega times rad A squared minus X squared. For part F, the free body diagram for the object going towards the equilibrium, the Fs would be pointing right because the force of the spring is always pointing at the equilibrium, and Fk would be smaller and pointing the opposite direction, while Fg and Fn are the same. And while the object is away from the equilibrium, the force of the spring would be pointing to the left towards the equilibrium, and Fk would also be pointing the same direction because the object is still moving right, so Fk is acting against it, and Fg and Fn are equal. For part G, this is the graph for scenario 1, and this is the graph for scenario 2. And we know that the period function is 2 pi times rad over m over k, and increasing the amplitude wouldn't affect the period. So for scenario 1, the graph will look like a negative cosine function, and for scenario 2, it would start at negative 2a, and scenario 2, the amplitude is bigger than the amplitude of scenario 1. For h, we know that the period formula is 2 pi times rad m over k, and you know that Tm is equal to 2 pi times rad m over k, and T3m is equal to 2 pi times rad 3m over k. And to make it easier, you can take out the rad 3, so it would equal to 2 pi times rad m over k times rad 3, and finding the ratio of T3m over Tm, it would equal to 2 pi times rad m over k times rad 3 over 2 pi times rad m over k, and 2 pi rad m over k would cancel on the top and bottom, so the ratio would be rad 3. For I, we know that momentum is conserved, so Pi is equal to Pf, and breaking it up, we get mv max is equal to 3 mv new max, because after the mass is 3m, and you divide both sides by 3m to isolate for v new max, and the m's would cancel out, so v new max would equal to v max over 3, and we know that v max is equal to a times rad k over m. And to isolate for a, we divide both sides by rad k over m. So a would equal to v max times rad m over k. And a m would equal to v max times rad m over k. And a 3m would equal to v nu max times rad 3 m over k. And we would plug in v max as v nu max as v max over 3. And we can take out the rad 3. And rad 3 over 3, you multiply the top and bottom by rad 3 to get 3 over 3 rad 3, and you cancel out the 3 to get 1 over rad 3. And a 3m would equal to v max over rad 3 times rad m over k. And we can take the am and plug it into a3m. So a3m is equal to am divided by rad 3. So we know that a3m is less than am. So So after the collision, the system loses energy and the velocity decreases. Therefore, the amplitude will decrease by a factor of rad 3.